Welcome to the next video in the series on condensed matter theory. In this video I want to look at a comparison between the exact solution, the Hartree-Fock solution, and a density functional theory solution for the helium atom. And we're not going to do any real numerical calculations, but just look at the forms and the possibilities that we have within these different methods. We know that the ground state that we have in Hartree-Fock theory is the state that is single Slater determinant representable with the lowest energy. So we can say by the Aufbau principle that we create an electron in the 1s orbital with spin up and a 1s orbital with a spin down out of the vacuum. And we can optimize now the radial wave function for this s orbital such that this state has the lowest energy. That then also defines a density, and with that density it defines a set of eigenorbitals for our Hartree-Fock system such that we can define now a basis set of one particle states, which are the Hartree-Fock orbitals with quantum numbers L and M and sigma, as we know for the atomic orbitals, very similar as the ones that you have in hydrogen, but now of course slightly different because the potential is not of a single hydrogen atom, but it is a nuclear charge of 2, but on addition there are 2 electrons sitting around, making an additional potential that is included in here as well. Still, this defines a basis set that is orthonormal and complete for bound states. We have to include the unbound states if you want to be completely complete. But that is good enough to work with and define now on this basis also the other wave functions. Our many-body state can basically be written down on the basis of these orbitals. So we're going to sum over all states where we create 2 electrons, one with spin up, one with spin down, out of the vacuum. One can have different principal quantum numbers. Well, the angular momenta in total must couple to 0, and that can only happen if the 2 electrons have the same angular momentum. And the same is true for the angular momentum projected on the z direction. For one electron it can be any value, but the total of the 2 must be 0, so they must be opposite. So we have to sum over n, n prime, l and m, and we have a complex prefactor n, n prime, l, m, which we combine the 2, and this of course is again a creation, such that we have a sum over single Slater determinants for our many-body wave function. Let's have a look at the wave function in density functional theory. In density functional theory we have quasi-particles, but let's now just take the Hartree-Fock orbitals for the basis set of the quasi-particles. We do not have to have the same orbital in Hartree-Fock or in density functional theory as we had for Hartree-Fock, so we can make a linear combination of the orbitals with different principal quantum number. And we have to have the same wave function for spin up and spin down. And we have 2 electrons in the s orbital just by conservation of angular momentum. So we know that our wave functions can be written down in this form for both the Hartree-Fock, the many-body ground state, and the density functional theory wave function on the basis of cone-sham orbitals. These creation and annihilation operators have a different meaning than those, but they can still be written down on the same basis set of functions. We can make a few statements that we know, and let's start with statements on the energy and then statements on the density. I know that I have a variational principle and that the ground state, or the energy of the ground state, is the lowest energy. So by all means the many-body energy must be smaller or equal to the Hartree-Fock energy. We also know that if our functional is exact, the density functional theory energy is the many-body energy. Well, the exact functional is impractical, although for helium it would be nice. You can in principle go through an exact functional. It's all doable. Just because the system is so small. Then we can have a look at the charge density. So the many-body charge density as a function of R is a sum over n prime Lm nu prime lambda mu. We have two wave functions that you need when you calculate the density. It's psi times psi dagger or psi complex conjugated. We have an alpha n prime Lm, an alpha nu prime lambda mu, and then the combination of psi n Lm with spin up at R complex conjugated times psi nu lambda mu with spin up at R plus, and then for the spin down part, n prime Lm spin down at R psi nu prime psi nu prime, this is this is n prime Lm sigma down nu prime lambda mu at R, also with spin down. Yes, spin up with n, spin down with n prime. For the many-body density. So it's a sum over the different basis states that we have. The Hartree-Fock density is the easier one, because this is just a single Slater determinant. We're representing everything on a basis of the eigenorbitals of Hartree-Fock. So that is the 1s with spin up norm squared plus the 1s with spin down norm squared. And the LDA charge density is a sum over n and n prime, beta complex conjugated of n beta n prime, psi ns spin up at R, psi n prime s spin up at R, plus psi ns spin down at R, psi n prime s spin down at R. For the electron densities that we have for the wave function that is a product of two states that are sums over the basis orbitals with different principal quantum numbers and an s orbital. Now, if we have an exact functional, for the exact functional, we know that the LDA density of states is equal to the many-body density of states. Density. We also see that the Hartree-Fock density has only the 1s orbital, whereas the LDA density is a combination of the 1s orbital but also higher principal quantum numbers. These are more extended in space, so we can immediately see that if this is our helium nucleus, we have our Hartree-Fock density, and you can now look at the many-body or the LDA density. That should be the same, albeit with higher principal quantum numbers that are more extended. So we start off a bit lower. Let me take a nice contrasting color, and we go out a bit further in space. the real wave function is more extended than the Hartree-Fock wave function, or the real charge density is more extended than the Hartree-Fock charge density, but the LDA charge density, or the DFT charge density, which is the better statement here, should be the exact charge density as a function of R. Now this allows us to understand a few approximations and effects that we see in Hartree-Fock, as our wave functions are normally smaller in Hartree-Fock than that they are in real life. You should find that things like bonding distances between atoms in Hartree-Fock are smaller than that they are in real life, just because the system is more condensed. Whereas in density functional theory, where you have more options to make the density close to what the real density is, for an exact functional they would be the same, but in our approximate functionals they are not completely the same. For LDA, the density is roughly in between the Hartree-Fock and the many-body density. If you use LDA, where you fit to the homogeneous electron gas with interactions to get your exchange and correlation functionals. But you see that the atoms become larger, or the densities around the atoms become larger, and therefore bond lengths become larger and closer to the real many-body solution that one should find. And you also see that by not optimizing just to the ground state in a way that you would normally do in a Hartree-Fock mean field, but by saying, well, I'm going to give myself a bit more freedom in how to determine that potential and talk about quasi-particles that not necessarily represent real electrons, such that also the kinetic energy is not necessarily just given by the p-square operator, h bar squared radians squared over 2m, but by some correction to that, you do have the options to get better results when you compare to experiment. Thank you very much. That's all that I wanted to talk about on how to calculate effective potentials. You should realize that whatever you do, it's always an approximation. And I think from the way I've treated it, that it's very clear that it is an approximation and that you have different choices that you can make for that approximation. And the question on how to make these approximations exact, especially in a controlled manner, is something that we will discuss about in basically the next semester. What I want to do in the rest is, well, we've started now on a basis of plane waves, free electron-like, and I want to first relate this to the atomic properties, where we can do then tight binding, and then also include things like disorder to really calculate what scattering times are and where they come from. And we do that on a basis with Green's functions, and the nice thing is that this language is also the language that you can use to treat many-body physics, because you really do not want to go to writing down many electron wave functions. But if you know how your system responds, how it may make perturbations to it, that in principle gives you the same information as you have when you know the wave function, now not only for the ground state but also for all excited states, and where the ground state density in principle determines your complete system. If you know all response functions, you also can in practice know the complete system and determine the complete system. So that's the outline how we will go in the rest of this lecture. Thank you very much. Of course, there's I say thank you very much and then I continue. There's many more one can talk about for the different types of functionals, but for now this is enough. Stay healthy. We see each other later.